So we will finish up chapter 20 today, and we are going to talk about a very interesting reaction in this section, where we are going to have a carbon ion to add to an alpha beta unsaturated carbonyl compounds, and we call this reaction the Michael reaction. Stabilized carbon ions, such as those that are derivative from beta diketones, they undergo conjugate addition to alpha beta unsaturated ketones. The typical Michael donors are beta diketones, beta ketone esters, so you can have the same reaction with the beta ketone ester, malonic esters, beta ketonitrile, and nitro compounds. In this reaction, we will be able to form a CC bond, and this reaction is very useful. As you know, if I have, for instance, beta keto ester, and I generate the anion of this beta keto ester, the enolate, this enolate is stabilized by resonance. I can do that if I have, for instance, the diethyl malonate, or if I have the ethyl acetoacetate. So I have these two enolates to be stabilized by resonance, and that enolate or this enolate can undergo Michael addition. Now the second starting material is going to be an alpha beta unsaturated aldehyde or an alpha beta unsaturated ketone. It is our first example. So what we have here, we have diethyl malonate. You're reacting it with KOH. This is a Michael product. So I'm going to go over this reaction step by step. What you have is a diethyl malonate. And you are reacting it with potassium hydroxide. So you are generating the enolate. And then the second starting material that you have here is an alpha beta unsaturated ketone. The alpha beta unsaturated ketone will react with this enolate, and you will get the 1,4 addition product. So the enolate is going to attack this carbon. You will have double bond, and you will have O minus. So what you have is CH, C, double bond O, O ethyl, C, double bond O, O ethyl, and you have CH2, CH, double bond, C, O minus, CH3. Now, you added KOH. So the O minus is going to abstract the proton from water, and you will form this product, which will tautomerize into the keto Now, if you take the Michael addition product and you perform saponification and then protonation and then heating it up, you will be synthesizing a ketone. So if you add, which is on the next slide, KOH and then H plus and then heat, what will be the product? Well, with the KOH, so upon KOH, let's do it step by step then, the saponification. So you will get CH2, CH2, C double bond O, CH3, and you have CO2 minus, CO2 minus, then H plus, you're going to get CH3, CH2, CH2, CH, CO2H, CO2H. And if you heat up, you will get rid of one CO2 group, and your product is C double bond O, CH3, CH2, 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 C double bond O, O, H. Any questions? So if you take the Michael addition product and you subject it to the saponification first, and then H3O plus, and then heat, you will be able to synthesize this product. Any question? Okay. Well, here is another example. You have this diketone now. And you are reacting it with an alpha beta unsaturated aldehyde or ketone. Here it is a ketone. How are we getting this product? Again, we're going to go over the mechanism of this reaction. You have this diketone, CH3. You're reacting it with the KOH. Of course, the most acidic hydrogen in this diketone is this hydrogen, because the enolate right here is stabilized by resonance. So you have O minus. To abstract this hydrogen, let's draw this resonance structure now. And you are getting this enolate. Now you're reacting this enolate with the alpha beta unsaturated ketone. So you have CH2 double bond CHCO CH3. It will undergo a 1,4 addition. 1, 2, 3, 4. Now what you are going to form, double bond O, CH3, CH2, CH, double bond, C, O minus, CH3. Then, with water, or methanol, you have here methanol as well. It doesn't matter if you write, you're picking the proton from water or methanol, because they are of comparable acidity. You're getting COH, double bond CH, CH3, excuse me, CH2, double bond O, CH, 3. Then this is going to tautomerize, and you will get this product. Now, if you have this product and you reacted with the sodium ethoxide, for instance, then you are going to have an intramolecular aldol condensation. So you started with the Michael addition, and then you have an intramolecular aldol condensation, and the product will be the result of a reaction that is called the Robinson annulation. You will be able to get a ring. So if you take this product, you can perform a Robinson annulation. A Robinson annulation is simply a sequence of a Michael reaction followed by an intramolecular aldol condensation. The result of this reaction is usually a 6-member ring. So if you take this and you react to KOH methanol, we got that. Now, if you take this and you react it with the potassium hydroxide, this is your product. How? Well, now you are adding KOH. This hydroxide ion is going to take this alpha hydrogen. You will form double bond, O minus. So the enolate that you are forming is this one. Then you are going to have an intramolecular aldol condensation, O minus, 2, 3. And what you're forming now is another 6-member ring. Please number your carbons. 1, 2, 3, 4, 5, 6. This is 6. This is 1. This is 2. This is 3. This is 4. This is 5. You have a double bond over here at carbon number 1. You have a CH3 group. 2, it is a CH2. 3, it is a CH2. 4, you have a carbonyl. 5, it is a CH2. At 6, you have O minus. Then with water, you're going to get that O minus protonated. If you heat it up, or even at room temperature in some reactions, you are going to get an elimination so that you will get a C double bond C to be in conjugation with the C double bond O. Now, this is the carbon that has the OH, so we need to look at the beta hydrogen with respect to that carbon. Either this beta hydrogen or this beta hydrogen. Of course, we're going to take this hydrogen out. We do not have any hydrogens here to eliminate. And the product that you will form is this product. This is a Robinson annulation product. What we performed here is a Michael addition and then an intramolecular aldol condensation. Do you have any questions? Yes, sir. You have a hydroxyl group. We're going to eliminate. We can eliminate either this beta hydrogen or this beta hydrogen. We do not have any beta hydrogen here. The C double bond C here is not in conjugation with the carbonyl. The C double bond C here is in conjugation with the carbonyl. We eliminate so that we get C double bond C in conjugation with the carbonyl because we agreed that the compound will be more stable. Conjugation will increase stability. And most of the time it happens spontaneously. That's right. Yes, ma'am.
I just want to make sure when we first added the KOH in the aldol condensation, so why did it attack the CH3, not any other acidic hydrogen?
Okay. You mean in the first step or in the second? Right here, let me just talk about the entire reaction. Right here, we agree that this hydrogen is the most acidic hydrogen, right? Because the enolate is the most stable. Now, between here, when you are having this product and you are adding a hydroxide ion, well, if you take this hydrogen, for instance, and you are attacking this carbonyl, you're going to have a bridged system. You're not going to have a fused system. And the same for this hydrogen. If you take this hydrogen, you're going to get a bridged system. Fused system is more stable. Now, when you are looking at this carbonyl, because we're looking at our alpha hydrogens in all, everywhere. You attack this carbonyl, you are going to have 1, 2, 3, 4-member ring. Fused system, but it is 4-member ring. The only hydrogens that will lead into a 6-member ring and fused system are these hydrogens. Any other question? Yes?
In the exam, for example, if you give us this starting material and you use KOH in methanol and heat, we are supposed to give you directly the product, the final product of the annulation?
Yeah. But I will put first KOH and methanol, then KOH and heat. Any other question? Okay. There's one more reaction. So this is not going to be isolated. You're going to have the elimination all the way to get the conjugated system. One more very interesting reaction regarding the 1,2 addition and 1,4 addition, or the addition to the conjugate addition. It involves the use of organocopper reagents. And you can use these organocopper reagents to form carbon-carbon bonds by also conjugate addition to alpha, beta, unsaturated ketone. If you take the dimethyl lithium cuprate and you reacted with an alpha, beta, unsaturated ketone or an aldehyde, the cuprate is going to add 1,4. Cuprate is large in size, it's going to attack this carbon. So you are having the source of CH3 minus, it attacks right here. You're getting C++C, O minus will be protonated water, and then you are having tautomerism, and you will get this ketone. Any questions? Okay. Now what we're going to do is very interesting. What we're going to do right now, we are going to take a product and we need to find out what are the starting materials using the reaction that we learned. What are the necessary starting materials for the following reaction? So the majority of you answered 4, which is 2 and 4. How are we going to solve this? What do you think is the best approach to solve this? Retrosynthesis. This is coming from where? From this one. Where do I put the OH? Right here? Or right here? Or right here? Right here. And you also have CH3 group. Now this comes from what? You must be breaking the bond right here. This is a C minus, right? The enolate right here at this carbon must be attacking the carbonyl, correct? So you are having this diketone, you have a CH3 right here, and you have CH2, CH2, C double bond O, CH2, CH3. This is the carbon that is attacking this carbonyl. Then this is coming from where? You're breaking right here. So it's coming from this diketone plus CH2 double bond CH, C double bond O, CH2, CH3. So this is number 2. And this one is number 4. So the correct answer is 2 and 4. And the majority of you got it right. Next question. What are the starting materials for the following reaction? Okay, I'm going to close the poll. So we got a rainbow of answers. And it looks like the majority of you are answering 3 and 6. So let's go over it. Retrosynthesis. Where is the OH? Is it on this carbon or on this carbon? This carbon. Then we need to break the bond. Do we break it here? Or do we break it right here? Right here? Fine. We are going to try both. CH3. So this is your minus right here. CH2. Another CH2. Another CH2. Carbonyl. Count the number of carbons. Let's say this is 1, 2, 3, 4, 5, 6. So this is 1. This is 2. This is 3. This is 4. This is 5. This is 6. And then where are you going to break the second bond? Between 5 and 6. You break right here. And you are going to get double bond O, CH2, CH3, CH3. So these are the carbons 2, 1, and 6 in the original product, plus number 5, 4. This is 5. This is 4. This is 3. And here is our oxygen. To test it, the best way to do it is to do the Michael addition, do the intramolecular aldol condensation, and find out if you are going to get the product. Now, if you take this 6 and you attack right here, you're going to get minus, double bond, then O minus. You're going to protonate it. And then you're going to have tautomerism. And then you need to do intramolecular aldol condensation. Now, what about breaking the other one? Why not? We take this OH. So let me draw it under it. What about breaking the other bond? So you have double bond O, CH3, and OH. Carbons 1, 2, 3, 4, 5, 6. What about breaking it over here? Because these are the only two possibilities. How can you get the alcohol unless you have the C minus to attack the carbonyl so that you will get an OH? If you do that, what are you going to get? You are going to get double bond O, CH3, double bond O. This is carbon number 3. This is 2. This is 1. 1 is attached to 6. 6 is attached to 5. 5 is attached to 4. This is the carbon that needs to attack, right? Isn't it? So that you form a bond between 4 and 3, you need a minus here. So this means you are having here a CH3. What is the problem with that? The hydrogen are not acidic. They're not alpha to any carbonyl. Right? To have the enolate attacking the carbonyl, you need to form an enolate. You need to have acidic hydrogen. These hydrogens are not acidic. They're not alpha to any carbonyl. So you are having number 3. And your ketone is number 6. So 3 and 6. The correct answer is 9. So the majority of you got it right. Okay, next one. What is the major product of the following reaction? This question was part of the last organic competition.
بس الاكسبيرمنت شويه سعيد.
Okay, I'm going to close the poll. So 16% answered 1, 12% answered 2, 20% answered 3, and 52% answered 4. Well, with LDA, what are you getting? The kinetic enolate. So you are getting O minus CH3, and then you are reacting it with this aldehyde, the conjugated alpha beta unsaturated aldehyde. So what you're going to have, O minus, this double bond is going to attack this carbon, and then you're going to get O minus. So what are you going to form? Double bond O, CH3. And now let's call this is 1, 2, 3, and my oxygen is number 4. This is attached to carbon number 1 that has CH3 group. Number 1 is attached to 2, which is attached to 3, which is attached to O minus. So this is number 1, this is 2, this is 3, And I have a double bond between carbons 2 and 3. And then I am getting CH3, C double bond O, CH3, OH, double bond. And then what are you going to have? Tautomerism. CH3, CH2, double bond O, H. So the correct answer is 4. 52% of you got it right.